Did anyone do this or not? No? Okay. Well, what do you think we want to do if we want to try and eliminate the parameter? What did we do in yesterday's example that had sine and cosine? So basically, we want to try and write this and eliminate the t. You know, t is, so this is parametrically defined, and both those functions are continuous, right?
Or y equals 25.
25. Sine. Am I that hard to hear? Maybe that guy was just saying hi to me.
With the wrong finger.
Yeah, that wasn't the, yeah, I know, that wasn't even to me. It's like, leave him alone. This is a bad idea for you. But anyway. All right, so what did we do yesterday? What do you think? Squared them. All right, so we can say, hey, x squared plus y squared, right? If I do that, I'm going to get 4 cosine squared t plus 25. What? It's 25 there? 25 squared is 625, right?
So it'll be 16 cosine squared t.
It should have been. It was 4 squared cosine squared, yeah. Like that, that's x squared plus y squared. It doesn't really work out very good, does it? So actually, so we can't factor out the same number, right? So that's a little awkward. So what? But he said, hey, if I want to square cosine, where did that go? Did you see sine squared t?
Yeah, I see it.
But then it disappeared. Did you see it disappear?
No, I didn't see it in the first place. It just showed up just now.
All right. Well, good. Yeah. So I'm obviously having connection issues. But anyway, I can divide both sides by 4 on that side. I can divide both sides by 25 on that side, and then square both sides. Can I do something like that? So now it's going to be x squared over 16 plus y squared over 5, right? Or x squared over 4 squared equals. So anybody know what that graph is? Like if you have, I think the theorem, or the if you have x squared over a squared plus y squared over b squared equals, would equal 1, right? I believe. But anyway, this would be an ellipse where you go over a and left a for the x's, right? And then up b, down b for the y's. And anyway, it ends up being an ellipse like that. So in this case, it's going to equal, I'm going to be over 4 and left 4, and then up 25 and down 25, right? That makes sense?
Yep.
So it's an ellipse. And then is there any restrictions on whether x is positive or negative? So like, in other words, is it possible that we only have the right half or the top half of the ellipse? Okay, so t is an element of 0 to 2 pi, including 0 to 2 pi. So that's fine. Now what happens with cosine from 0 to 2 pi? It's positive and negative, right? And what happens with sine? It's positive and negative. So we get the whole thing. Okay, but we do have to pay attention to that. Does that make sense? All right, all good with that, so I can move on. Let's move on to some new stuff. Let's move along, and then I've got to cover. I've got till 10:29, or what time?
Yep.
Huh? 29.
Yep. I can hear you now.
Use the chat function when you can't hear me.
All right.
All right, but anyway, so we were talking about curves. So I do want to finish this. you've got the definitions on page 781. 781. So one was talking about a smooth curve, right? So if we have a smooth parametric curve on a closed interval, basically f prime and g prime are continuous. So we've got x equals f of t, y equals g of t. So parametrically defined, and t is an element of a to b, including a to including b. All right, so that's obviously t is an element of these of that interval. But the way it's smooth, if we say that the curve is smooth, and once again, Isaac had a good description of that yesterday, no sharp turns or points or things like that. But anyway, if f prime and g prime are continuous on that closed interval a to b, and we need one other thing, they're not both 0. Okay? So f prime and g prime not both 0 on the open interval a to b. Okay, so that was smooth. So we talked about that yesterday. So examples of smooth curve, you know, so basically, you know, here's you know, that would be a smooth curve. That's a smooth curve. Curve. By the way, start point to end. What is the start? Would be f evaluated at a, right? That's the start point. And the end point would be f evaluated at b, g evaluated at b, right? Does that make sense?
Yep.
All right, so you saw that? So those are smooth, all right? So we had that,
Yep.
but then we also had closed. Basically, if the start point and the end point is so basically, I'm just going to call this point A, and I'm going to call that point B. Can I do that? Instead of writing f of A, g of A, and f of B, g of B. We could also, if you wanted to shorthand it, we could write x sub A, y sub A, which really we can think of that as x evaluated at when t equals A and y evaluated when t equals B. We could do that, something like that. But anyway, if so we have smooth, but then we also have closed. Okay, so it's closed if the endpoints are the same. So in other words, point A equals point B, or in other words, f of A, f evaluated at t equals A and g evaluated at t equals A is equal to when t is equals B. So what does this say? This says that f of A equals f of B and g of A equals g of B. So it's closed if start point and end point are the same. So this is an example of something that's closed, right? So what's something that's not closed? I have something like this. This is not closed. That's pretty obvious, right? And I'm putting a little arrow on where I go. So they call it the initial point. Terminal is the end point. All right, so we had that yesterday. We also have simple. We need to define a simple curve. Basically, a curve is simple. So the curve, parametric curve C is simple if and only if there's no multiple points that are the same. All points are distinct is one way to say that. Another way to say no points are the same. Okay, so that'd be a simple curve. No points are the same on the open interval. So if I pick any point in between, I'm only going to hit it once. I'm only going to hit that once. So let's just look at a simple curve. So let's look at a couple that we've already had. What about something like this? So we talked that's smooth, right? There's no sharp points if I drew it right. But so it's smooth, right? Is it, can you hear me, Luke?
Yep.
It's not closed. Is it simple? Yeah, it's simple, right? Okay, well, let's look at another one that we've already had. Let's go this way. This is smooth, right? Is it closed? Yeah. Then you say, okay, well, what's an example of one that's not simple? Here. Anyway, because of this point right here, which I'll use a different color, that point right there, two different inputs give that as an output, right? So two different values of t would give that. So this is simple, right? Is it closed? No, not closed. Is it? It's not simple. It's smooth. Is it simple? No, it's not simple. I didn't do that on the last screen, did I? Write simple first? I don't think I did. I can't see you, so you got to talk to me. All right. Anyway, let's look at another one. How about this? Let's just infinity. Let's do the infinity sign. And let's just kind of go this way. I don't know if that's the way I went, but going this way. What about this one? What can you say? Is it smooth? Smooth, yes. Is it closed? Yes. Is it simple? Not simple. Okay, all good with that? So I think that's all you need there for those definitions on curves. And then now we're going to go, let me go back to black. Basically, if you remember the chain rule, remember the chain rule? We had dy dx is equivalent to dy dt times dt dx. So we kind of had that dummy variable in the middle. Remember that? And we thought, hey, it's kind of like canceling fractions there. And it ends up being like dy dx. You remember that? Now we could rewrite this. The book rewrites this a little bit differently. They write it as dy dt over, we could, instead of multiplying by a fraction, we could divide by the reciprocal, right? So we could rewrite this as dy dt over dx dt. Everybody agree? We can do that. Then, of course, we could do this with the second derivative. If I want d, sorry, let me go back to black. If I want d squared, second derivative of y with respect to x, okay? Well, that's the derivative with respect to x of dy dx, right? Which we could call dy dx, we could just call that y prime, right? So it's the derivative of y prime divided by dx, dy prime over dx. And of course, we know what y prime is. Y prime is what this one is, right? So we could consider it this way as well. So if I plug, this is y prime, so dy prime. So we could also rewrite this then, the second derivative, d squared y over dx squared, second derivative of y with respect to x. We can say that that is the derivative of y prime, dy prime dt over dx dt. Now you might say, well, why isn't that an x prime on the bottom? Because it's the derivative with respect to x of, so basically that's the only one that has the prime in it. Okay, so then we're going to come up with the next one, so I at least want to get through this section. today, as far as what I want you to do. So it's asking us to rewrite parametric equations, find the derivatives without eliminating t. Okay. So instead of doing examples in the book, should we do an odd? You want to do an odd? How about number 11? Should we do number 11? So number 11 says to find dy dx and d squared y dx squared without eliminating the parameter t. So in other words, we were on the previous ones, we were eliminating the t's, weren't we? Now we're looking at instantaneous rate of change, which why do we do that? Then we can see where there's a horizontal tangent line or vertical tangent line. So that type of stuff, so it can help with graphing. So that's part of why we evaluate derivatives for instantaneous rate of change. But on number 11, we've got x equals 3t and y equals 2t squared. Okay, and it says find dy dx without eliminating the find dy dx. Well, we want to just use that definition of basically utilizing the chain rule and say, hey, that's like dy dt over dx dt, correct? Do that, what's dy dt? 4t. And what is dx dt? 3. Over 3, right? Now if I'm doing the second derivative of y with respect to x, once again, we have dy prime over dt all over dx dt. So if I do this, what do I get? Well, the derivative of y prime with respect to t, that's the derivative of that thing with respect to t. So this is equivalent to 4/3 t, right? What's the derivative of that with respect to t? 4/3 all over dx dt is what? 3. Okay, just like it was before. 3 over 1, 4/3 times 1 over 3, 4/9. Okay. We got t squared e to the t. All right. Anyway, dx, dy dx, sorry, dy dx. Anyway, if I want to do this without eliminating the variable, right, it's dy dt over dx dt. So basically, we just got to do that. All right, dy dt. Let's do that one in red, shall we? I don't have yellow font like the yellow belly that I saw last night. All right, so first times derivative of the second, derivative of natural log is 1 over, right? Plus the second times derivative of the first, derivative of t is 1. All right, so anyway, this nicely cancels out to just ones. So anyway, this ends up being 1 plus natural log of t over the denominator, dt. I got to use the product rule here as well. So it's the first times derivative of the second, derivative of e to the t is e to the t, plus second times derivative of the first is e to the t times 2t. So what I might do is I might just factor out a e to the t or a t e to the t, and I'm left with t plus 2 there. So that is the first one. And then, of course, the second one could be, and I'll let these high school captive students leave, and I'll finish the second one out on this. I just need to remember this. So can you repeat that to me if I need it? I think I'm okay.
Yeah, I can.
So dy dx. Okay, and I like to put a little loop on my t so it doesn't look like a plus sign. But anyway, now I want second derivative without eliminating the parameter, which is going to be the derivative of y prime with respect to t over dx dt. Okay, dx dt is t e to the t times t plus 2, right? That one, because we already did it before. But go back to red on this. So we got, oh, no, the whole thing. This is dy dx is y prime. So this is y prime, right? So that's the whole thing. So for the derivative of y prime with respect to t, I got to take the derivative of that whole thing. So ultimately, I have to use the quotient rule, right?
Yeah.
So, which isn't very fun, but we'll do it. So bottom times the derivative of the top. So t e to the t plus 2 times the derivative of the top, which would be derivative of 1 is 0, derivative of natural log of t is times 1 over t, right? So the nice thing here, those t's will cancel out, minus the top, 1 plus natural log of t times derivative of the bottom. I got to need that in parentheses. Derivative of the bottom, I might rewrite that out as multiply that out. I don't know if that's going to help or not. T squared e to the t plus 2t e to the t. Derivative of the bottom, we got to use the product rule for both, don't we?
Yep.
So that's getting pretty ugly pretty fast. What number is this? 13?
13. Yep.
All right. So not very fun. And then we'll, this is where I need my board so I can see things. Anyway, so bottom times derivative, or no, what did I do on the first one? Bottom times derivative of the top. Okay, we got that. These, I'm just going to simplify this out here, but this t and this t cancel out, right? Minus the top times the derivative of the bottom. All right, so the derivative of the bottom is, should we use the product rule? I think instead of having it multiplied out over here, let's just go ahead. This is a product. The derivative of the right one is going to be pretty easy. The derivative of the left one, we're going to have to use the product rule again. But anyway, so it's first. So I'm going to consider it t e to the t by itself, and then t plus 2 by itself. So it's first times derivative of the second. So t e to the t times derivative of the second is just 1, right?
Yep.
Plus the second one, t plus 2, times the derivative of the first. Okay, so the derivative of the first, I'm going to do in blue here. I got to use the product rule again. So it's the first times the derivative of the second, which is t e to plus the second times the derivative of the first. T plus 2. All right, so let me try and rewrite this better down here. On top, what do I got? I got e to the t times t plus 2, and then minus 1 plus natural log t times, and then I got to figure out what's all in here. This is t e to the t. I got to multiply this out here. So I'm going to do this. This is t squared. So if I multiply the t through there, t squared e to the t plus t e to the t, and then plus 2t e to the t plus 2 e to the t, right? and that's that part here, if I did it right. And so what was left, I still had t e to the t up here, but I've got t e to the t, that's 2t e to the t plus 2t e to the t, right? Hopefully, for those. And then I've got plus t squared e to the t for that one, and then I have plus 2e to the t for that one. So I got all that, and then all over the denominator. So this is all over the same denominator, which is t e to the t times t plus 2. Right?
Yep.
All right. So question is there an easier way to write this out? I can get a whole bunch of stuff. If I consider this as two different fractions, I do have yellow. Look at that. Yellow belly, I'm coming after you. All right. So anyway. Two, but I could use rules of fractions here, right? So if I do that, let's see, what color haven't I used yet? Green. So I've got e to the t times t plus 2 for the left side of this fraction, all over t e to the t times t plus 2. So this works out swimmingly well because those will cancel to ones, these will cancel out, and I get 1 over t. So that's 1 over t here. And then minus, I got on the right, I've got 1 plus natural log of t. And then what I'm going to do here is I'm going to pull out, I can't pull out a t, but I can pull out an e to the t. So I'm going to pull out an e to the t and then see what's left. And I'm going to write it in descending order. So I've got 4t plus t squared plus 2. So I'm going to write that as t squared plus 4t plus 2 in descending order. Right? And then this is all over the denominator, which is t e to the t times t plus 2. And what's nice here is the e to the t's would cancel out. Does anything else cancel? This doesn't matter because that'd be t plus 2. That doesn't have any real number factors. It's entirely on or above the x-axis. So I believe it would just be minus 1 plus a natural log of t times that all over t times t plus 2. So anyway, so this the left side is 1 over t, and the right side, I'll just put this in gray, is 1 plus natural log t times t squared plus 4t plus 2 all over t times t plus 2. And then that should be my final answer. And no idea if, let me see. We could, I think if this is an odd, was this an odd exercise?
Yep.
So I believe that the book would actually try to get a common denominator here. So they would multiply top and bottom times t plus 2. And then they have a common denominator, so you could put it all over, final answer, all over t plus 2. No, somehow they still have an e. They have an e to the t somewhere still.
Yeah.
Didn't I get the e? I thought I got the e to the t's cancel out everywhere. So I don't know. But anyway, so, and then this would be t plus 2. Try this out, each spot out each spot and then try and simplify. But long story short, I kind of liked what I had when I first put the gray box around. But if you really want to try and see if that matches up with the book, we can. I'll double check my work because I don't think it agrees. I think the back of the book has a E to the T, but I will double check that before I stop the recording.
Yeah, it does.
So yeah, I don't know. I don't like it. I might draw that up on the dry erase board so that way I'm a little more secure on. Did we agree with the first derivative? Because if we didn't agree with first derivative, that could have been a problem.
So
9.1 number 13. I believe, yeah, we did agree with the first one, didn't we?
yeah,
So I'll go back, double check the work, but it could be possible that the back of the book is wrong, and I just don't know it yet. So anyway, I'll stop